Hello everyone, I'm Peter Connolly. I'm an independent consultant, mostly specialising in geomechanical simulation using finite elements. Um, Collaborate an awful lot with the sponsor of my presentation, Outer Engineering, and I'll be talking today about the impact of geomechanics simulation and how HPC can really be used to improve our industry-wide efficiency. Um, So there are numerous places for HPC to address efficiency across the whole of the whole of oil and gas product stack, if you like. There are many, and that's probably too few many's moving parts in oil and gas. I'm not going to go through any of them in this left side, but just hit on a couple of high spots that we really can address with in high performance computing in the upstream, and that's coupling new and existing simulators together and the benefits that would come from that. What's a little bit our touch, because we've got such short time, a little bit our touch on what we need, but mostly just the value add that that could bring. And then how, and most importantly, integrating our engineering simulations to bring workflow improvement and really help us move the asset forward for business success by building a very robust basis. And then there's, of course, the traditional high performance computing opportunities that we're all aware of and that have been widely used and will continue to be used and improved upon across oil and gas, but particularly in the upstream and midstream, the mid and downstream. And we've been using these for a long time. They're some are very mature workflows, some are very new, but there are many of them, and we can definitely carry on and improve those. Again, by integration. So what do we need in upstream simulation? And the big problem we have really is that upstream simulation, the vision is to get to this whole Earth model where everything is all encompassed in one simulation space. Unfortunately, we have all these separate models, the reservoir model, the basin model, the mechanical model, and even a seismic model. And many properties, different material responses, but they're not always integrated. For example, static moduli that's used in a basin model might be very different to being used in a mechanical Earth model. What static to dynamic transformation might be used to go from our seismic model to our mechanical model. All of these things are rarely coherently pulled together. The big workflows that we mostly use at the moment, what happened there? Is that we take a seismic interpretation, we turn it into a geometry, and that geometry forms the basis for standalone different models, all with their own deliverables and things. And there's no iteration, there's no feedback loops between these, except when we realize, oh, well, model X isn't suitable for task Y. And then we go back and look at our geometry and eventually say, oh, it's been updated, that was wrong. We need to redo our seismic, and then we go through the whole loop again, and that's massively inefficient. And it's not what happens in the wider high performance and engineering disciplines across other industries. We're really dropping the ball significantly in earth science in general, but particularly in our industry. So this leads us on to wondering what the requirements are for simulation, and obviously I've only covered a couple of them here. They're both technical and computational. And one part I'd really draw your attention to and that we're going to focus on are really these geometric changes that occur as the asset evolves, as we drill it, as we find new seismics, as we deplete it. Those are both inherent geometric changes caused by inaccuracies in our original data set that we can update, but then things like depletion and compaction within the reservoir can cause other geometric changes. So we have to be able to update our volume. Obviously, there are other technical aspects to it. And then on the computational side, particularly, we have to make our computational approach correct for the size and the scale, or the scale and scope of the project the business decision we're trying to make. So we really have this technical limitation, I think, which is the geometry. We can't modify that readily. And then we have the technical scale and scope for our computational implementation, as well as the other issues I've highlighted. One critical part I'd bring up is that for the longest time, we've had this good enough mentality, particularly around simulation, and that really limits and focuses the simulation into one very narrow direction that isn't broadly applicable across the asset and is very difficult to transfer from one deliverable to another. And so it makes that whole Earth model idea very difficult to realize. Two quick examples of how this is all important. Here's a pre-drill seismic volume with a top reservoir here. We drill a well, and lo and behold, rather than our top coming in at this blue horizon, we find that it comes in 30 feet or so shallower at the top of the structure. And of course, as we go off flank, that gets a little bit thicker. And so we have this big delta in the volume, or approximately 60 foot. This is obviously a synthetic example, but about a 60-foot variation in the thickness of the reservoir. In this trivial example, that gives us with those silly numbers, about 10 million barrel difference, and at $50 a barrel, roughly what we're at. Okay, yesterday it went higher. $500 million plus all the costs of actually doing reprocessing and all of that stuff, but also the time lost. That's 6 months to a year lost on the asset and all of those things. And if you're making a decision, is $500 million enough to go or no go, and you've got lead time for a rig or a platform and all that, that's a huge amount. This extra cost is, significant change. So this geometrical uncertainty has huge economic implications for the asset and for the oil and gas industry. Do we need to reprocess it? That's a philosophical question. Of course, at some point we will, because we'll need an updated and improved volume, because we've got the velocity and massively better velocity model if we've got one well in the ground. If we've got three, that's even better. So yes, at some point, but how and when and how many times? And then, can high performance computing offer any alternatives? Well, one that's used across almost every other industry except ours is tokenization of geometry. And that's where we assign mathematical functions to our in our case, it would be interfaces or fault surfaces. And we can change these as a simple function, change a couple of parameters in our expression, get different configurations, and they, of course, would yield different responses as we load them with whatever system we're using. So this tokenization is massively used in other industries, but why not in geoscience and in oil and gas typically? Well, number one thing, of course, is our geometries are extremely complicated. This is obviously a salt body, which shows 2 of 3 good points. You can see how rugose and how changing and how uncertain our geometries are. There's uncertainty around every little part of this. And obviously, the bigger uncertainty on the vertical surfaces or the steeper surfaces than on the lower angle surfaces, just because of the nature of seismic. But we have this geometric complication because the forms are difficult. And then, of course, we also have these huge aspect ratios. So this is where we're let down by this image, because if we just put a thin layer horizon above this, and worse would be a 3-way trap against it, we have massive distance laterally, but very short distances vertically. And that gives us these huge aspect ratios. And that means that in addition to having numerous horizons, we need extremely high resolution, which gives us element counts that are really pushing the limits. And so that means that to get to tokenization, not just the computational complexity of the geometries, but also the scale at which we are working, really requires HPC as it is currently. And then, of course, there's many interactions, complexity, faults, intrusions, etc. And something that isn't always mentioned, but we don't have unique inputs. Our geometry has uncertainties, our material properties have uncertainties, our spatial variation of material properties have uncertainties, our pore pressure model has uncertainties. So all of those, we have non-unique inputs, and of course that gives us non-unique outputs. And the non-uniqueness in output is also we have multiple places where the outputs are trying to go, so we have to somehow pull them together. So we have many different products desired from our stations. One final quick thing is, at the moment our simulations are done in this way, very much as shown in the first thing, where we start off with geometry models, and that just drives all these other models, which sometimes they have intercommunications with, sometimes they don't. The vision, and this is nothing new here, is to have this much more iteratively coupled with all the tolvers talking to each other and the geometry. So you feed back to that geometric uncertainty, and you can bring that into AI or machine learning and design of experiments to handle all those uncertainties. So geometry becomes an uncertainty variable. All of this stuff, it should be very clear, needs high performance computing. It's just massive amount of information that need to be filtered rigorously and then also integrated. And we have to use both the information we collect in the subsurface, so the machine learning and all the data science work that's going on, but also still recognize that deterministic simulation and design of experiments using that is an important thing. This says very much the same thing, just in a different format, where there's this huge overlap. Is if we could tie basin, reservoir, and mechanical models together, we'd end up with this thermo-hydromechanical coupled systems. And there is lots of work that's been done, and particularly in academia and the national labs, those scale of institutions. But in a commercial sense, really there's nothing available that can solve this problem right now. So what would the value add be all of that? Well, at the moment, each of our little simulation things gives us a little bump in our value, but we really want to build on those previous pieces of value and keep them growing. And so we end up with a much better value of HPC throughout the whole thing. So, by tying the models together, as I've suggested, we'd continue rather than drop after the seismic and the exploration phase. And then when we integrate all of this early simulation with the knowledge from the asset, we can really make another big stump by tying analytics and machine learning and deterministic simulation together. And of course, there's a big gap. There's a big market potential there. So what's the biggest problem or thing that we can bring from other industries into oil and gas? And that's really to address this data shuffle gap, which other industries, manufacturing industries, just-in-time manufacturing, all of those type of things have really been working very hard at for 30 plus years. We need coherent information transfer between the different dimensions, unit systems. I mean, can you believe units are still a problem we all handle, and you spend, 5% of a technical project managing units. Clearly, data can transfer between different simulators and different input structures. So whether that's from seismic, whether that's well information, and then how we tie those things together, whether it's fully coupled, loosely coupled, uncoupled, all of these things, all of the issues around those. I mentioned a couple of times that we need to tie the machine learning aspects, the design of experiment, deterministic thing, to really get a much more coherent, continually evolving picture of the subsurface and what we're doing to the subsurface and how it changes it, and also how we interrogate it. So this data simulation and interrogation all needs to be interoperable. Sorry for that tongue twister. Of course, to make that interoperability thing, result analysis, I haven't touched on that at all, but we really need to get better result analysis ones, not earth science or engineering. We really need to have everything available in one place with numerous ways to look at it. And, at the moment, we always struggle with the proprietary formats and shuffling stuff in and out and all of those things. At least we have got some big efforts going on now that maybe will improve that. there's much progress, especially in other industries, but we really haven't pulled those into our industry, and that's I think a thing. And I think that if people aren't offering ease of transfer of information and things, maybe we as purchasers of software should be looking at other industries and other places which have solved many of our things, if not to actually buy software, at least for partnerships and for inspiration on what we could improve in our systems. So with that, hopefully I was on time. And I'd like to once again thank Altair for sponsoring that, and I'll take any questions.